Hello, everyone, and welcome to our IEEE 802.11ax training series. We are very pleased that you've decided to join us today. My name is Jennifer McLean. I'm Senior Manager for Education Products with IEEE Educational Activities, and I will be helping to moderate today's event. IEEE is the world's largest technical professional organization dedicated to advancing technology for the benefit of humanity. Please note a few housekeeping items before we get started. At the bottom of your screen are engagement tools that are resizable and movable, so you can move them around to make the most out of your dashboard space. If you have questions for today's presenters, you can submit them through the Q&A widget on your screen, and we will answer as many questions as time allows. If you click the green resources icon at the bottom of your screen, you'll find more information about IEEE 802 standards and IEEE e-learning courses. And finally, the on-demand links for today's event will be emailed to everyone approximately 2 hours after we finish today. IEEE Standard 802.11ax is the latest step in a journey of continuous innovation in the wireless local area network standards, and is the underlying technology of the latest Wi-Fi 6 products. Unlike previous amendments to the 802.11 standards, such as 802.11ac and 802.11n, which were focused mainly on increasing the peak throughput, 802.11ax focuses on achieving higher efficiency and improving metrics that reflect user experience. In this training, we will provide an overview of the features and optimizations introduced by 802.11ax physical or PHY and medium access control or MAC layers. Day one, today we'll focus on the MAC layer and the PHY layer rather, and tomorrow we'll focus on the MAC layer. Our presenters today are Bin Tien and Alfred Astorjadi. Bin is a Senior Director of Technology and Wireless R&D at Qualcomm. He currently leads the Wi-Fi physical layer system team, which is responsible for R&D, prototyping, and standardization of Wi-Fi technology and solutions. Since 2012, he has contributed significantly to different generations of 802.11 standards, including 802.11ah, 802.11ax, 802.11ba, and 802.11be. Alfred is a system engineer in wireless R&D at Qualcomm. His focus is on the design, standardization, and performance evaluation of MAC protocols in wireless systems, with a special emphasis on increasing efficiency, scalability, and reducing power consumption in wireless networks. He is the chair of 802.11be and has served as the vice chair of 802.11ax and vice chair and technical editor of 802.11ah. We welcome everybody, and I will now turn it over to Alfred and Bin to get us started.
Okay. Thank you very much for Jennifer's introduction. Alfred, I'm very excited to come here and to introduce the 802.11 standards, which is basically the foundation standards from what's so-called Wi-Fi 6. So before we dive into the details of the standards, 11ax standards, but let's zoom out and start to look at the Wi-Fi. Okay. So Wi-Fi now becomes an essential part of our daily life, especially if you have kids. I think some kids will tell you that they cannot without food, but they want to have Wi-Fi. So if you think about it, Wi-Fi, in fact, just showed up almost 20 years ago. The first IEEE 802.11 standards was adopted in 1997. Then it have a tremendous growth over the last 20 years. Okay, so annually there are over 4 billion devices shipments, and this number keep going up. And Wi-Fi now, as I mentioned, become an essential part of everybody's daily life, not just at home, your work, in retail, enterprise, and in all the venues. Okay, if you look at the Wi-Fi all this year's growth, it's very clearly there is a clear trend. Okay, The first of all, it grow from single band 2.4 gigahertz, then grow to multiple band, 5 or 6 gigahertz band, we'll talk about today, and also go to sub 1 gigahertz and even the millimeter wave band, which is 60 or 45 gigahertz. Okay. Another direction they're going through is the higher throughputs. Okay. There are a lot of these amendments we'll talk about is focus on higher throughput, especially at the beginning of the Wi-Fi standards development. Okay. Focus on peak throughput, introduce MU-MIMO, and also the later, which is the focus of this 11ax, which our topic today, is the network throughput in the dense environment. Of course, the better coverage is another focus. Not only the traditional Wi-Fi to the each devices, we can show here in the right hand, you can see the Connect TV, phones, media devices, appliance, secure camera. Okay, now it's also going to outdoors. Okay, going to the mesh and also go outdoors and also going to the indoor mesh to improve the networks. Okay. There are a lot of, as the Wi-Fi application keep growing, there are also a lot of demands on reducing latency and reliabilities, and Wi-Fi also did many works in this area. I think in today's or tomorrow's discussion, you can tie to many features along to that direction. Of course, power is also very important. Okay. Everybody wants their phone charged in the morning and to come back still with enough batteries. Okay, so a lot of power optimizations in the Wi-Fi standards. Also, the enhanced security. I think recently the older WA3 mandated to ensure everybody have a peace of mind when you use the Wi-Fi. And with this technology keep improving, you will find all these new applications based on the Wi-Fi keep booming. Okay, right-hand side, I show many of use cases. Okay, nowadays, beyond the traditional communications, new applications also come in nowadays, positioning, eye sensing, wake-up radio, all these kind of things. So overall, Wi-Fi industry have a rapid growth and try to expand to all different kind of part of the applications and greatly impact our daily lives. Okay. This is a very high-level view to provide you idea what the Wi-Fi technical evolution. Okay. So in fact, when you talk Wi-Fi, in fact, there are two series of terminology. First one is the standards, IEEE standards. Okay, generally speaking, you will call it 802.11n, AC, 11ax, 11be. That's the amendment number that's built by the IEEE. Okay, there is also the term called Wi-Fi, which is coming from the Wi-Fi Alliance. Wi-Fi Alliance is sometimes you heard term Wi-Fi 6, which is based on 11ax standards. We are talking about it. And the future Wi-Fi 7 is built on the 11be, talk about it. So Wi-Fi, terminology of Wi-Fi is coming from Wi-Fi Alliance, and each of these Wi-Fi generation is built on one of the main amendments or standards coming from IEEE, okay? Of course, IEEE Wi-Fi standards, there are many cover maintenance specs. Here, we just highlight the few most important ones. There are many other things I want to add it in the IEEE that build on each part of the improved Wi-Fi performance, okay? So go back to this chart. You can see that around 2009, you will start to see the 11n product, okay? 11 product is called Wi-Fi 4 in the current marketed term, okay? 802.11 is named, standard name, in fact, is called high throughput, okay? When you evolve into 2013, then go to 11AC generation. 11AC, the IEEE name, in fact, called VHT, very high throughput. will go to the 11AC time, the peak throughput already increased to 6.9 Gbps and introduce a channel 160 or 80 plus 80 megahertz and introduce the downlink to MU MIMO. Okay. And in the 2020 timeframe, which will be a subject, the 11ax, which is the subject of this training, show up, complete the standards and products that start to ship. Okay, 11ax is one of the big changes from previous generation. 11ax is named, in fact, is called high efficiency. So introduce many of the features, OFDMA, uplink MU MIMO, scheduled MU, transmissions, A transmission, and also introduce the 6 GHz band support, okay, which all of them will cover in today or tomorrow's training. Okay. And beyond 2020, IEEE working on something called 11BEE, okay, which will become the future generation of Wi-Fi 7. In the future, this standard is still being worked on. Hope we are targeted finishing the next year. So once it's done, then hopefully actually we have another training like this so we can introduce everybody about the standards details of this one. Okay. So beyond this 2.45 and 6 GHz band, another big effort is on the 6 GHz band. In that one, there are 11AD and 11AY. Okay, all of them try to explore the millimeter wave band and try to provide very high throughput and very low latency applications. Okay. By the way, this is just the main amendment we mentioned here. There are a lot of other things because of time limit and space limit we didn't mention here. One of them, for example, is 11AH, which is targeted for the sub 1 gigahertz, a lot of IoT applications. Okay, so overall, this is kind of a roadmap, the evolution map. You see the Wi-Fi technology. It goes from the growth of the throughput, now go to the higher density, high efficiency. Okay. So IEEE 802.11, its official name in the IEEE standard, in fact, have name is called high efficiency, HE Wi-Fi. So in the future, in the slide, you will see many places we call HE something. Basically, HE represents high efficiency. When the 802.11 project was approved, there is something called PAR, basically defined what this project going to do. Okay. This is, we copy the scope of the PAR here to give people an idea what this project about, okay? You can see it want to enable the mode of operation to support at least 4-time improvement in the average throughput per station in the dense environment scenario, while maintaining and improve the power efficiency per station. So essentially, when we design these 11ax standards, we are trying to look at how to improve the efficiency, especially in the dense environment scenario. So that's the name high efficiency come from, okay? Of course, while we are doing this, we also try to keep the power efficiency in mind, okay? Of course, every this one will define operation in frequency band from 1 gigahertz to 7.125 gigahertz. So this is the range of 11ax operate on. Essentially, if you look at this frequency range, there are 3 essential bands: 2.4 gigahertz, 5 gigahertz, and 6 gigahertz band. We'll talk later. Okay, and for every generation of the IEEE standards, okay, we'll try to ensure the backward compatibility and coexistence with the legacy devices. So, if this is the standards, if you look at standards, so as I mentioned, WFA, which is the Wi-Fi Alliance, based on their product certification based on IEEE 11ax standards. There's something called Wi-Fi 6, which is the first wave one of the Wi-Fi 6 feature. And in the 2019, that was launched in 2019, and the end of 2021, which they launched Wi-Fi 6E, which is Wi-Fi 6 plus 6 gigahertz band support. And last year they will launch Wi-Fi 6 Wave 2, which is more features on top of the Wave 1 release of Wi-Fi 6. Okay. So this is a rough timeline of how 11ax standard was developed. Okay. The PAR, as I mentioned, basically is how this project is defined, was happening around 2014 March. Then after that, the IEEE formed something called the task group to work on these standards, and it's generate the first draft, which is draft 1.0, and trying to circulate around the working IEEE 802.11 work group. They called a letter ballot for the review and the comments. So the first draft happened around 2018. Then there are many rounds of comment and revise, review process. Then once you go to 2019 and 2020, this standard becomes stable in the working group level and is submitted to the IEEE standard body, association body for approval. This is in January 2020. Then essentially it's published in 2021. Okay, so before we dive into the AX, I want to give a little bit of teasing tips as what's happening beyond AX, which is what the IEEE standard currently working on. What they're working on code is 11BE, which is have a name as extremely high throughput. Okay, this 11B is the next major one project after 8.11ax, and the scope of 11B project, if you look at from the PAR, what we code, it's called PAR Project Authorization Request. Okay, will enable the maximum throughput to around 30 Gbps, and also try to improve the worst case latency, and also try to improve the band device operation, and also compatible operation between the 2.55 and the 6. Okay. Then the next generation Wi-Fi product, okay, based on 802.11be, we'll call the Wi-Fi 7. Okay, we expect the Wi-Fi 7 will be launched at the end of this year. Okay, you will start to see the product showed up. Okay, so again, this is just to give a preview, just to see what we're going to discuss for the 11BE, which is one beyond the next generation, beyond the current AX one, which future one. We talk about 320 megahertz. We have a 4K clamp to improve the peak throughput. There are something called multiple RU aggregation and preamble puncturing. Some of the basic concepts we'll discuss in today's and tomorrow's 11AX training, and the 11B basically move further beyond this. Okay, trying to further improve it. Okay. There are also 11B introduced something for the CGS improvement for the low power indoor channel enhancement. Okay. There are also something called the multi-link operation. So now you have so many bands. How do you this multi-link work coherently and try to work together to reduce the latency and throughput? There are also a lot of other low latency enhancement, quality of service traffic characterizations, restricted targeted TWT, trigger single user scheduling, emergency preparedness communications for EPCS. So a lot of interesting stuff in the future. Okay. when this standard is ready, hopefully IEEE will have another training course on this topic, and people can cover and learn on this new development. Okay, so that's the overview of the Wi-Fi history, evolution, and what 11ax about, and how do we get to, and what's the future beyond AX. From now on, we are going to dive into the AX training and AX knowledge now. So let me see if any of the questions here. Okay. Okay. I see a Q&A there to see how do you verify the standards working at per expectation between working group and IEEE SA Ballot? Is it with industry support? Yes, I think the IEEE task group, I think, has a wide participation between the standards and academia. So between the working group and IEEE standard ballot, okay, there are many rounds of revision, and people will do the performance simulation verification to make sure the performance is as expected. Okay. Okay. So with that, let's start talking about the main focus of today or tomorrow's training, which is 802.11ax. And in the topic 2 in this section, before we dive into details, we want to first highlight the main 5 features introduced in 11ax and their benefit. By the way, if you already haven't been figured out, I think today's topic will mainly focus on the 5 topic, and tomorrow the Alfred going to focus on the 11ax max part. Okay. So the first big changes for the 11ax is introduce a new 6 GHz band support on top of a 2.4 and 5 GHz band. Okay, most people are familiar with wireless LAN, which is the IEEE standards or the Wi-Fi, know the current product already support 2.4 and 5 GHz band. In the 11ax timeframe, where we developed the standards, regulatory bodies start to open up the 6 GHz spectrum. Okay, this is the big thing for the Wi-Fi industry, because the new spectrum allows to support much more applications, throughput, relieves congestion of the Wi-Fi. Okay, there are around 1,200 megahertz, so huge number of the new spectrum was released in US, Canada, South Korea, Brazil, and many geographic countries. Okay, in some other part of country, half of them, for example, 480 or 500 megahertz, okay, of new spectrum we released in EU and Japan. Okay, while there's some other geographic regions still working on it, they're not available. So the spectrum availability of the 6 GHz band is still not global available, but now more and more countries are opening up. So major geographic regions, most of them already can enjoy this new 6 GHz band. Okay. So as I mentioned, 6 GHz band in fact start from 5925 to 7125 megahertz range. This is the 6 GHz range. Okay. So IEEE defined the 6 GHz channel plan start from 5945 megahertz, so leave the 20 megahertz guard band at the lower end. And when you define this one, basically you can derive the channel center frequency basically based on this formula, 5950 plus 5 times the channel number. Okay. In 11ax time, IEEE defined the 20, 40, 80, and 160 megahertz channel. Okay, and you can see the first channel of these different channel widths I given in the slide here, 1375. Then you can correspond to channel center frequency based on the above equation. 320 megahertz is defined in 11BE. I didn't draw it here, but I just want you to be aware that 11BE time, which is standards beyond AX, we will further expand this channel plan to include 320 megahertz here. Okay. The plot here, we give a brief drawing of what the channel plan looks like. This drawing, okay, there are two icons here. One is blue one, the other has the yellow one. That's just to show in the U.S. Situations, because in U.S. the channel signature channel was divided into two types of channel. One is low power indoor (LPI), the other is LPI plus standard power. Okay, which I use the blue and the yellow. Okay, there are lots of details. Feel free to reference to the regulatory rules. But the big news is that for AX time is that the Wi-Fi will now enjoys much more spectrum in the signature span. Okay. Now let's talk about PHY efficiency. Okay, the high efficiency. How do we achieve high efficiency? Which is the name of 11AX. From PHY side, we did many things. The first thing about the link efficiency. Okay. 11AX introduced a new OFDM numerology and the tone plan. Okay, we use a 4x longer data duration. Okay, if most people here is familiar with 11AC knows 11AC, 11N. When you have a date symbol, if you don't look at the GI, have a symbol duration 3.42 microseconds. Okay. For 11AX time, now we make the 4x symbol. So we make the symbol duration without GI become 12.8 microseconds. So essentially, which means when we have this longer symbol, okay, it enables us to do two things. The first one, we can pack the more data tone percentage round to 11N or 11AC for the same bandwidth. I will provide you, for example, for 11 and 11AC in the future, you will find there for the 11 11AC 20 megahertz, okay, you have only 52 data tones, okay. For the 11AX, because we have a 4x symbol durations, we have 256 FFT size and we have 234 data tones within the one symbol. So the percentage of the data tone is much higher than AC for the same bandwidth. And also we have less relative guard interval overheads due to the longer symbol. Because we all know guard interval is determined by the delay spread of the system. So for the same environment, the guard interval will not changes. But because we have a longer symbol duration, the date symbol duration, the relatively guard overhead will drop. Okay. Another way we do this, improve it, is on we introduce 1024 QAM, which is 25% of the peak throughput more than the 250 QAM, which is the 11AC. So here I provide a big table there, the table here to compare the support peak data rate for each bandwidth, assuming given A spatial streams. You can see compared to 11AC, 11AX have a significant improvement on the peak data rate, giving the same bandwidth and the same number of spatial streams. Another thing, 11AX improved on the Wi-Fi link is on its robust enhancement. Okay, The first thing you do is try to extend the range. Okay, it's trying to. We'll cover this later in the slides in the training. Essentially introduced as the extended range mode. In that range mode, it can provide 3 dB better link buttons for preamble, and it can do even better for the data portion, 6 dB better for the data portion, because sometimes the data portion can have much more data than the preamble. So we have much more data, generally a little bit more link margin than the short data. Okay, this is the reason, in fact, you can improve the more for the data portion than the preamble part. 11ax also introduced a new modulation called something called the dual carrier modulation. Acronym is the DCM. The basic idea is the DCM is based on name, the dual carrier. Basically, it duplicates the same information on 2 separate subcarrier. So from this duplication, essentially you halve the data rate for the same MCS because due to duplication. However, from this duplication, you provide the half the data rate, so you can provide the link budget gain, we call repetition gain, and also many times when you do the duplications, you do the diversity gains. If one part gets highly faded or the interference, you still have another part. Okay. Also, 11ax also do have a better outdoor support because have a longer GI mode, introduce a longer GI mode. 11AC, the longest GI 0.8 microseconds, which is very good for all this indoor environment, but it will go to outdoor. Sometimes the echoes, the reflection come from very far distance apart. So we will, of course, issue for the OFDM modulation. So 11ax introduced the longer GI mode to accommodate such environment. Also, 11ax also have some feature called mid-amble support. If you have this high Doppler environment, that you have outdoor, you have a lot of vehicle passing by, then the channel reflection from that vehicle change a lot. In that cases, 11ax provides something called mid-amble, so that in the middle of packet, you can receiver can use that mid-amble to refresh the channel. Okay. So one of the main part 11ax to improve the efficiency in the dense environment is trying to provide a more flexible frequency and spatial multiplexing method. Okay. One of the big things introduced is called downlink uplink OFDMA. So essentially, what it means is that it's serving multiple devices simultaneously in different frequency resources. Okay. So OFDMA essentially try to divide its resources, in this case is the frequency, into multiple segments. Each segment we call the resources unit, and you can assign resource units to different users so that you can do in one transmission, you can address different devices simultaneously, okay? By introduce OFDMA, you can introduce efficiency, you can reduce latency, and it's ideal for the low bandwidth applications, so you can serve many low bandwidth applications simultaneously. Another direction that 11ax improved is to try to serve multi devices in the different spatial streams. In other words, all these devices, they share the same frequency, they're the same time. However, they're separate on the spatial by doing what's so-called MU-MIMO, multi-input, MIMO technologies. We can separate the different stations together differently, okay? So, 11 MIMO technology, the downlink MU-MIMO technology was first introduced in 11AC. In 11ax, we we expand this MIMO technology first to the uplink, and also we do some minor improvement on the downlink MU MIMO, so that it can be more flexible to scheduling and to set up the group and trying to do the MU MIMO transmission. Okay. By the way, we can see MU MIMO. Generally, you can transmit a lot of stations simultaneously in the spatial. Okay. MU MIMO need to set up, need to sounding. So generally, it's good for the high bandwidth applications. Okay. 11B AX, we still support up to 8 spatial streams. Okay. 11AX also try to improve the efficiency in the high density environment by introducing the new spatial reuse schemes. So people familiar with 1111AC know you have this traditional concept of CSMA, conditional avoidance. You have the CCA. Okay. Now the 11AX, people think about try to reuse the spectrum more often, try to enable more shared transmission opportunities, okay, between overlapping BS service set, OBSS, in the dense environment scenario. So essentially, two types of spatial reuse operation are defined. One is called OBSS PD-based spatial reuse. We'll talk about it in the future. The other is called parameterized spatial reuse. It's short for the PSR. Okay. Also, the preamble puncturing concept is introduced in 11AX. Okay. Simply, you can think about the puncturing is when you transmit the physical layer packet, and some of the 20 megahertz within the band has interference, it's busy. 11AX time, it start to allow the transmission that puncturing out those busy channel. Okay. 11AX, by the way, I want to mention, start to support this preamble puncturing, but very limited. The full function of 11 preamble puncture was supported in the next generation, which is 11BE. Okay. One more thing that was introduced and support in the 11AX is also better support for the IoT devices, what we call the narrowband stations. Okay, they define a few terms here. The first one is called 20 megs only non-AP station. Essentially, this just meant client devices that hardware or the software capability only supports the 20 megahertz bandwidth PPDU packet. Okay. There's another definition called 20 megahertz operating non-AP station. This essentially means the device either is the 20 megahertz only devices because of its hardware capabilities, or it's reduced its operating channel to 20 megahertz temporarily using some operation mode changes we called OMI to save power or this kind of things. So in other words, 20 megahertz operating devices is just to describe the devices operating currently only can be operating with a 20 megahertz bandwidth, either due to its hardware limitation or due to its true to do because of optimization for power or other factors. Okay. Similarly, we also defined 80 megahertz operating devices. Okay, just like the 20 megahertz operating devices, such devices either capable of up to 80 megahertz or choose the operation bandwidth 80 megahertz. Okay. So assume you have a Wi-Fi network that AP can set up a bandwidth of 80 or 160 megahertz BSS. Okay, this network has such wide bandwidth. Now you have a lot of narrowband devices here, 20 megahertz operating, 80 megahertz operating. So in this network, you want to utilize entire bandwidth together instead of just to use the 20 or 80 megahertz that station only supported. So in these cases, it's better to transmit to these narrowband devices in the wideband OFDMA so that we can address those 20 or 80 megahertz devices only in this supporting bandwidth, while we can give rest of the spectrum to other stations. So 11ax introduced this kind of two mode. 20 megahertz operating devices participate in downlink OFDMA with wider bandwidth, 40, 80, 160 megahertz. Okay. And 80 megahertz operating devices participate in the 160 megahertz bandwidth. So this is just to better support IoT and for the system efficiency. There's some minor IU assignment restriction because for the devices have DC tones in different tones cause some file challenges, but those are the details you can find from spec. But overall, you can see 11ax much better support IoT devices from efficiency point of view in the 11ax. Okay, so this is the overview of what we have, from PHY side, all this efficiency improvement from link, multiplexation, spatial reuse, the robustness, all this support IoT. These are the all main directions that 11ax have done to improve the PHY efficiency. We will cover them in the formula section. But before we dive in the details, any questions, comments? Okay, I didn't see any question in the chat window. Okay, so hopefully everybody can try to refresh your mind and try to think about it. What are the main 5 features introduced in 11ax and how they related to the PHY efficiency? Okay, let's move on to the topic 3. Okay, from now on, we're going to dive into the main section of the 11ax file. We're going to go over all the details. Okay, the first main thing is about the numerology. Okay, the tone plan, IU structure of the data portion of the 11ax. Okay, we just mentioned that in the 11ax standards, okay, we redesigned the entire OFDM numerology for the better efficiency. Okay, we mentioned that now we go to the 4x symbol durations. Okay, I think many times you see this kind of terminology is the 4x symbol duration. 4x is relative to the numerology of the 11AC, which is the previous amendment of IEEE. When you have a 1x symbol duration, you have the day symbol without GI have a symbol duration of 3.2 microseconds, which I showed in the table below. When you have a 4x numerology, then your symbol duration without GI become 12.8 microseconds. Okay. So because we use a longer symbol durations, the first one, as we mentioned, the GI size now becomes a smaller percentage over the symbol time. For example, 0.8 microsecond GI, which a typical GI duration for indoor environment is 25% overhead for 11AC and only 6.25 for 11ax date symbols. Okay, and also have a better tone utilization because we redesigned the numerologies. Okay, now we have 4x symbol duration. then the subcarrier width, we show the table here, shrink from 312.5 kHz to 78.125 kHz in the 11ax time. So that allows you, for example, for the 20 megahertz, now you use, instead of 64 point FFT, now you use 256 point FFT. And with you have more tones there, you can locate, have a little bit less tone location for this kind of overhead tones, which I mean the guard tones, the DC, all the pilot tracking tones. So as an end result, when you go to the new numerologies, it gives you the better spectrum efficiency. Okay, so for example, in the 20 megahertz 11ax have 234 data tones, which is 95% of all the FFT tones out of the total 256 tones. Whereas in the 11AC time, you have 52 tones out of total 64 tones. Okay, it's 81%. So you can see just because by doing this numerology and we have a 10% higher efficiency spectrum utilizations. Of course, for different bandwidths, this improvement is different, but overall, as I've shown in the overview section, in the previous section, because the tone plan changes, okay, 11 have the significant improvement on the file link efficiency. So, how do we mentioned that 11ax introduced the longer symbol duration have more tones. Okay, we have introduced efficiency. We also mentioned 11ax introduced OFDMA. Okay, OFDMA essentially means orthogonal frequency division multiplexing, multi-addressing. Okay, that's the MA part. Okay, essentially it just means you locate small part of the we have a packet occupy the entire bandwidth. Now you give the small chunk of the subband of frequency into different users. Okay, from that point of view, 11ax defined the term called RU, resources unit. Okay, resources unit is the bunch of the FFT subcarrier of FFT tones you locate to one station. Okay, that in OFDMA transmission, okay, we can have different RU. We have 20 megahertz, 40, 80, 160 megahertz transmission. Each bandwidth, you can define the different RU size with that 20 band, which bandwidth, and each of these RUs is assigned to different stations. Okay, one RU is assigned to one station. So 11ax, you can see it defined the following RU size. It defined the 242 tones, roughly corresponding to 20 megahertz, 484 tones, roughly corresponding to 40 megahertz, 996 tones, roughly around 80 megahertz, and 2 times 996 tones, roughly correspond to 160 or 80 plus 80 megahertz. Okay. There are also some small RUs, which is less than 20 megahertz RU size. We have RU size of 26 tones, 52 tones, 160 tones, roughly correspond to bandwidth of 248 megahertz. As mentioned in OFDMA transmission, each RU with each station was assigned to one RU. Okay. And for MU-MIMO transmission, we only support for RU size larger than 6 tones, so at least 10 megahertz, because MU-MIMO transmission is supposed for high bandwidth. needs to set up. Is for high bandwidth applications need to set up. So MIMO transmission we only reserved for the high bandwidth. At least needs 10 megahertz, 10 megahertz, which is 6 tone. Okay. So in the following table, I list for different RU type, each bandwidth, how many RUs that it has to give you idea. For example, for the IU26, you have 9 IU26 in the 20 megahertz, 18 in 40 megahertz, blah, blah, blah. Okay. So how this IU is located. Okay. So remember, okay, just for we draw the plot of IU plot for different the bandwidth package for the 11ax. Okay, 11ax. Remember, it's called HE, high efficiency. So those packages were represented by HE20, which is a 20 megs package, HE40, which is 40 megs package, or HE80, which means 80 megs package. Okay. For HE20 packet, imagine this is HE20 packets. Okay, they have OFDM symbol, which uses 256 FFT. Okay, so which means in the OFDM symbol in the frequency domain, you have total 256 subcarriers. Okay, we call 256 tones, which is after FFTs. Okay, for those tones, okay. If you look at HE20, it shows how this each RU size was located within the 256 tones after FFTs. Okay. If you look at the top, it shows this RU26. It's from beginning, they have the left-hand side some guard tones, which is yellow, so that to meet a mask requirement. After that, you have two RU26. After that, you have some RU no tones there because there are some extra tones which now needed. They have some another RU26, two RU26 RUs there. Then after that, there's some center RU26 which is cross DC. Then in the center of FFT, there's 7 DC there. Then after that is the other side of DC. So the first layer is all the RU26, how they located. Then after that, you have RU52, RU16, RU242. Okay. So when you do the OFDMA transmission, so either you transmit RU242, which takes all the HE20 tones, or you transmit one RU16, you take all the tones on left-hand side of DC. Then you transmit center IU26, or you transmit the IU52 at the right hand of DC, blah, blah, blah. So you have all this kind of very flexible, this IU combination, you can support it in the HE20, 20 megahertz. The similar things I showed HE40, okay. Now you have more IU26, IU50, IU60, 242, and IU44, which is 40 megs PBDU, IU, and the IU80. This gives an overall idea how these tones are located. And also the high efficiency, the IU16080, I didn't draw here. It's essentially the same as HE80 and the duplicated of the other 80. So what each RU looks like, we talk about RU is basically just a bunch of the tones, continuous tones after FFTs, okay? So each RU consists of two parts of tones. One is the data tones, the other is pilot tones. Data tones mainly carry information, while pilot tones are used for the tracking purpose, okay? For the face tracking or this kind of thing, okay? So here I list all the different bandwidths, RU26, 52, L6, blah, blah, and tell you the RU size. and the number of data tones there, and number for Pioneer tone there. Okay. And how this, we know the data tones will be determined based on this MCS, modulation and coding schemes. It will use the different coding scheme we talk about in the future, and different modulation. So how about the Pioneer tones? Okay. Pioneer tones, in fact, is shown transmitted in that location, basically transmitted a known BPSK sequence. We call it the BPSK Pioneer sequence. Okay, and this Pioneer sequence is a fixed, but is vertically circularly shifted one Pioneer tone from one OFDM symbol to a symbol. So in other words, suppose you have four Pioneer tones. The sequence, the value is A, B, C, D for the first symbol. The next symbol will become B, C, D, A. So the same sequence from symbol to symbol is keep shifting. So, okay. And also the Pioneer tone, the date symbol, what we so-called is single stream Pioneers. Okay. This is relative to the data portion. In the data portion, when you transmit in MIMO transmission or the MIMO transmission, okay, all the data was basically use of something called pre-coding metric. The use of the purpose of that pre-coding metric is to split the data across a different spatial stream, so that the different stream have a different data we can achieve MIMO. Okay, multi-input, multi-operate. You can transmit more spatial stream, means more data in given the same frequency and time. Okay, but for the Pioneer, single stream Pioneer, when you transmit it, everybody don't need to split it because for tracking is use a single stream Pioneer. Okay, so where the Pioneer is located, here in the below the slide have a plot. It shows all the relative position of the Pioneer. You can see this Pioneer location is relatively consistent across the different RU size. Okay. Of course, some of the Pioneers, for example, RU262, RU26, you have two Pioneers every RU26. But when you go to the larger number of the RU size, like RU242, you don't need so many Pioneers. You don't need two Pioneers every 26 tones. So some of the Pioneers we reduced, but overall the Pioneer position, if present, is always consistent across the different RU size. Okay, so this is the end of the topic 3. Okay, we can do a quick Q&A. Let me see. Okay, in the Q&A. Okay, how is the tone defined? Okay, as I mentioned, the tone is basically reflect to the one of the FFT bins, because OFDM essentially you take date symbols, then you take the FFT. For example, you 256 FFT, each FFT bin is called FFT tones. Okay. So another question, what the disadvantage for longer symbol duration? Does that increase congestion, makes the channel more busy? No. Okay. So essentially what we're doing is that given the same 20 megahertz, okay, instead of 20 megahertz we send to the 64 tones, we make the 256 tones. So we basically means we pack the more tones in the certain bandwidth. It's not congestion because you still occupy the same bandwidth. Okay, and the downside of this we'll talk about in the future. We'll get to it. It makes processing a little more complicated. more processing time because suddenly you need to deal with a larger FFT, and we receive one symbol, there more data need to be processed. Okay, I think there is one more question is what is preamble punching difference in 11B come to AX? Yes, okay. We'll talk about the preamble punching in the future details. Okay, I think that's a main Q&A question regarding this topic. Let's take a 2 or 3 minute break for people stretch stretch your arms, then we will come back to the topic 4, which is one of the most dense section, a lot of details. So before we dive that, I want people stretch your arm a little bit. Then we'll come back around 10:03. Then we'll go to the next section. Okay. Okay, let's start, resume our discussion. I think now we'll get into topic 4, which we talk about 11ax PPDU. PPDU is shortened for the term Phi Protocol Data Unit. Okay, this is one of the most heavy part of this Phi training. Okay, a lot of details, but they are the most very useful one. Okay. So we'll talk about 4 types of the PPDU, HE PPDU defined in 11ax, and the usage and the details of each field of the HE PPDU. Okay. PPDU. Okay. 5-layer protocol data unit. You will see many of these terms in the specs, standards, Essentially, this just means the file packet. This is the unit that is sent in the file layer. Okay. 11ax defines 4 types of PPDUs. Okay. The first one called HESU PPDU. You probably can guess the SU here stands for single user. Okay. It's mostly used for the downlink, uplink, single user transmission. Okay. The second the PPDU is called HERSU PPDU. ER means extended range single user PPDU. Okay. So this PPDU was enhanced just for extended range. Okay. The third one is HEMU PPDU. MU here stands for multiple users. Okay. This MU I write as the mainly used for downlink MU transmission for the downlink OFDM and downlink MU MIMO transmission, but it doesn't include somebody want to use it transmit to a single user is still fine, but just more overhead in the signaling part we'll talk about in the future. But mainly usage is for all this MU, the good multiplexing scheme we talk about OFDM and MU MIMO. Okay. The last one is called HETB PPDU. TB here stands for trigger-based PPDU. It's used for the uplink trigger-based transmission, uplink MU MIMO, uplink MU MIMO. Okay. So we'll talk about in the future why the uplink OFDM and uplink MU MIMO need special treatment, need to use the trigger-based transmission. But for now, you just remember that for uplink, we have multiple station transmission. Okay. Either using OFDMA or MU MIMO transmission, you need AP to schedule it. Otherwise, all some transmission will be transmit on top of each other, nothing will get through. So we need AP to transmission to schedule it. So that AP is schedule what we something called the triggered frame. Basically trigger transmission. Then once being triggered by the AP, each station will participate in uplink OFDM and uplink MU MIMO and using HE trigger-based PPDU. These are the 4 main types of PPDU. There are some variant of this the PPDU. For example, there is something called HE sounding NDP. NDP here means no data PPDU. Essentially only have the LTF for channel measurement. We'll talk about in the future. This is just only for the sounding purpose, okay? This is just simplification of SU PPDU. There's something called the trigger-based feedback PPDU. It's a variant of trigger-based PPDU. This one is not widely used, so we not cover in today's training. But again, this is just variant of the most basic PPDU we're going to talk about today, okay? Before we dive into details, but I want to give the overall feeling about what this PPDU looks like. Okay, so this one I give you the HESU, HE trigger PPDU, HEMU, HERMU, SU PPDU. Okay, this slide is great, provides an overview of all the different parts of the different PPDU format. Okay, for example, from all of them, you know that the yellow part, what we something called the legacy preamble, start from L, LSTF, LLTF, LSIG. We'll talk about slightly later. This is something we call the legacy preamble. This is very essential for the coexistence with legacy devices. 11N, 11, and before 11N, or non-HT, all this kind of package based on that. Okay. And after that, you have all this kind of preamble in different color, repeat LSIG, HE SIG A, SIG B, And after that, it go to the HESTF, which is for the AGC readjustment. Now we go to the data portion. Then HELTF for re-estimated channel. Then go to HE data portion for transmitted data. Then we have something called packet extension. So this figure provides you the overall picture of what this packet is. And by the way, it also have a lot of details about how to differentiate the different packet format. Okay, we will cover in the future, but this slide is a very nice summary. In the future, when you learn the other following slides, when you forget about how to differentiate this, you can always go back to these slides and try to see, how these different slides, how different PPDU formats are differentiated, are classified, and what the different component it is. Okay, so on the higher level, actually PPDU field, including two parts. One is something called HE pre-HE modulated field. In that field, use 1x numerology with 4x symbol length. Okay, it's fixed, use a 3.2 microsecond plus 0.8 microsecond GI. Okay, and this part includes Lexi, STF, LTF, LSIG. By the way, in the right-hand table, we spell out what's the meaning of this acronym for each part of it, okay? And it also have IR-SIG, HE-SIG-A, signal field A, HE signal field B, okay? Then we have HE modulated field, okay? HE modulated field mostly use a 4x numerology, okay? For example, date symbol use 12.8 microsecond plus 0.8, 1.6, or 3.2 microsecond GI. Other field, HESTF, HETF, there are a little bit complication there, so it's not exactly this duration. We'll cover in the future, okay? So overall, it's divide all the HE PPDU field divide into this called pre-HE modulated field, use YX numerology, and HE modulated field start to switch to 4x numerology. All the tone index, everything switch to that. Okay. So let's look at the Lexi preamble first. Okay. Lexi preamble, all these things start from L, LSTF, LLTF, LSIG. Okay. And we also want to cover repeat LSIG here. Okay. So what are LSTF and LLTF? Okay. STF is short training field. Generally is used for the packet acquisition, for the course and frequency timing estimation. Okay. LTF is long training field, generally for the fine frequency estimation and also for the channel estimation, used for decode following the signaling field in the preamble part. Okay. This one I will not go over the details because this 11ax, this is exactly the same as in the previous generation, 11AC, or this kind of things. So it will be the same. The only thing different I want to mention is that for the ERSU PPDU, remember we have this PPDU format, this two portion at 3 dB power boosting, so that to make things a little bit longer, to have a little bit higher power to achieve the longer range. Okay. And there is some LSIG based on Lexi signaling field. Lexi signal field is for the Lexi packet to indicate the modulation scheme and the packet duration. When it's used for the 11ax, if the data rate field is fixed, okay, 6 Mbps, okay, the most important part of LSIG is it contains the length field to introduce the PPDU length. This LSIG is the foundation for all the coexistence between the different generation of 8.11 Wi-Fi packets. Okay, this LSIG is understandable by all these different generations. So each generation devices, if you don't understand other part of a preamble, at least you understand the length field of this preamble to tell you how long this packet is. At the bottom of this figure, I draw a figure for the MUPPDU. We can see the L length cover the entire length, start from L6 to the end of packet extension. So every station, when you got this length, it can back off and now transmit during this this period. Okay. Of course, this L6 we also add some signaling capabilities there. They're a little bit detailed. You probably don't need to worry about now. In the future, we got detail we can raise back. This L6, we do the modulo 3 operation. If the modulo 3, if the value equal to 0, okay, modulo 3 operation, then it's 11N, 11AC packet. If 11Y02, then 11AX packet, okay? 11A and G packet can be any other value. So this is the signature to differentiate the packet from the 11AX packet from 11N and 11AC packet. Okay? So we have something called the repeat L6. We know the all the legacy preamble, including L6, okay? 11ax introduced the concept called repeat L6. Repeat L is the exact repetition of L6, okay? It serves two purposes. The first one is used for the HE packet format detection. So receiver can just detect if there is the exact repetition of repeat L6 versus L6, then it can know this is HE packet. Okay. The second part is that any repetition can improve the budget of L6. Remember, we were down to extended range because ERSU want to be more robust. So repeat L6 save that purpose to make L6 more robust. Okay. Also, in the long delay spread environment, when you have repeat L6, it also serves better purpose that you have more robust in the L6 performance. So in other words, L6 is one of the important differentiation, introduce the 11ax, introduce the classification method, and also improve the link budget and also more efficiency and also robustness in the long delay spread. Okay, so I want to talk a little bit modulated tones. Okay, so generally speaking, all this preamble is sent every 20 megahertz. Each 20 megahertz content is independent. Okay, in the L6 portion, L6 portion, and RL6 portion. Okay, all these portions that the repeated every 20 megahertz. Okay. For 11ax, in order to carry more payload in HE6 portion, okay, 11ax add more full tones starting from L6 and repeat L6 to provide the channel estimation for the future L6 content. Give you example. Okay. In all the legacy, the standards pre-11ax, LLTF, LSTF, and the L6 all starting from 52 tones. Okay, LTF here to provide the channel estimation. So if you use next LTF, all the following data signal field can only demodulate to 52 tones. For 11ax, start from L6 and repeat L6, we add 4 actual tones at each side of the 20 megahertz, okay, to expand the tone to 56 tones so that start from HE6A, all these things can carry 56 tones, okay, for carrying more payload in the SIG field. Okay. So let's move to the HE-SIG-A content. HE-SIG-A is one of the most the important field in the signaling field because LSIG just tell you how long this packet is. Start from the SIG-A field is really get into uh, what all the information needs the phone info data portion. Okay. So if you break down the HE-SIG-A content, by the way, you can always go to specs. There's a huge table there about HE-SIG-A content for different packet format. But here, I just want to high level to summarize what this field's about, okay? The first of a few bits help to identify the different HE-PPDU format. For example, we have uplink and downlink bits tell you which direction this packet goes to. It have format bit to different SU PPDU from trigger-based PPDU. Okay. The second part, HE-SIG-A content part, is about the coexistent, and also for the reception to know what the most important information about this packet. For example, the bandwidth. Okay. 20, 40, 80, or 160 megahertz. And also have something called the BSS counter, okay? Essentially, this is trying to identify this transmission PPDU is from your own AP, or in other words, your own cell or your BSS, or it's from OBSS. OBSS, you can just think from other cell operated by other APs, okay? So there are 6 bits there to identify the BSS. BSS is the basic service set of this transmission. There is another field, the TXOP. TXOP is transmission opportunity. This is a MAC concept. Basically says this message exchange sequence, how long will be this message, instead of just one packet, this TXOP tells you the duration of entire this message exchange sequence. Of course, because of limit reasons, we only can afford to put 7 bits there with very coarse resolution, 8 microseconds or 128 microseconds. There are some details in the spec to tell you how to switch between these 2 resolutions. Okay. There are also some special reuse fields there that needed for the special reuse. Okay, we'll talk about in the future. The next important part of the signaling A field is about the transmission parameters for the subsequent field in the PPDU. For the SU and ERSU PPDU, this basically is including the transmission parameters for HELTF, HE data, and the packet extension field, telling what kind of modulation scheme, coding will be used, what kind of transmission scheme, STBC or MIMO or number of spatial stream, whether it's a beamform transmission, GI-LTF type, packet extension parameter. So all this whole 9 yards need to define the phone transmission is covered here, so the receiver will be able to receive the packet. For the MU packet, okay, MU packet, in fact, remember MU packet particularly used for different users, okay? For different users, for multiple users, you need to do assignments. They are much more complicated. More signaling need to carry it. For the MU PPDU, in fact, there's something called sorry, this is the typo here. I apologize. Should be the HE-SIG-B here. Okay. EXT is 11B is next generation. This the typo should be the HE, which is 11AX. Apologize for the typo. Okay. So for the MU PPDU, all this assignment and all this data transmission information, in fact, is carried in the SIG-B. Okay, so actually SIG-A only need to carry what actually SIG-B transmission parameters. Okay, for example, how long is actually SIG-B, or what modulation we use actually SIG-B. By the way, the HE-SIG-A, everything still like LSIG is the basic data rate. The start from HE-SIG-B, you can change the data rate. Okay, and also HE-SIG also carry another common information across all the IUs. It's not each IU specific, like the GI LTF type, number of LTF symbols, LTBC actual symbols, STBC, PE, all these kind of things. Okay. For the HE trigger based PPDU, in fact, it doesn't carry any information about phone field. It doesn't carry any assignment information, this kind of thing. It doesn't carry any of a transmission field information. Why? Because HE trigger PPDU information is scheduled by the trigger frame sent from AP. So AP already know all this kind of modulation information, LTF, all these kind of things. So intended receiver or PPU don't need all this information. So in other for HE trigger-based PPU don't have this kind of the parameter for subsequent field. Okay, it only have the information of the bandwidth, the classification, and all this special reuse information, and the BS counter TXOP. Okay, so how this HE-SIG-A is being transmitted? So HE-SU-MU trigger-based PPDU, what we transmitted, everything is the BPSK. Okay, I have a drawing here. We only have two HE-SIG-A symbols. Okay, so code HE-SIG-A, HA1, HE-SIG-A2. They're two BPS OFDM symbols. This is talk about the spec. Okay, they're all modulation by BPSK, 1/2 rate using the convolution code BCC. Okay, and have 52 tones there, data tones. Okay, 4 pilot tones, so there are total 56 tones there. There are two symbols there. The total, each symbol can carry the 26 bits. The two symbols can total carry 52 information bits. And the GI duration is 0.8 microseconds. It's same. By the way, entire pre-HE modulation portion, we don't change the GI. Okay. For the ER extended range SU, we have a little bit special. Okay. First of all, instead of two symbol here, we make it two symbol, and like other packet, we make it 4 symbols so that we can get 3 dB more reliability there. Okay. So besides the A1, A2, symbol A1, A2, which is carry 52 bits, then this information is repeated again in the A3 and A4. Okay. However, to increase the diversity, it's not a simple repetition of A3, A4. The A3 one is we change the interleaver scheme. Okay. A3 use the same interleaver, A4 with interleaver bypass, so that the repetition of A3, A4 don't have exact same bit pattern. There is one more thing to highlight by red there is HE-SIG-A, unlike all the other symbols use a BPSK modulation, it's modulated by the QBPSK. Essentially, QBPSK essentially just BPSK. Instead of transmitted phase of 0 and pi, you rotate by 90 degrees, you transmit at minus half pi and plus half pi. Okay. The reason we change the 90 degree here is just for the packet classification to different ERSU with the SU packet and other packet format. Okay. Now let's go to the HE-SIG-B portion. We know that the HE-SIG-B only present HE-MU PPDU. We mentioned all the other ERSU, trigger PPDU, SU PPDU don't have that because there's no need to assign to multiple users. HECG cover everything, okay? HECG carry resource location information. We have multiple users and their transmission parameters, modulation, coding, spatial stream, all this kind of thing. So from that point of view, it divided into two sections. Common field, which carries IO location information. IO location, whether it's SU, and for each IU, whether it's transmit for each IU, it transmits to a single user or HU or HRU, which is resource unit, by the way, or applied to different multiple users, become a MU-MIMO transmission. And if MU-MIMO transmission in that RU, how many users in that MU in that RUs? And HECB field is not presented for the full bandwidth MU-MIMO mode. This is something called HECB compression mode, because for the full bandwidth MU-MIMO, you don't need to the IO location. It's full bandwidth. So you don't need the common field portion, okay? The number of users for located to full bandwidth MU-MIMO is also indicated in HECB portion. There are some details there. We'll not go over that level of detail to go to spec, but just want to point out that for this special compression full bandwidth MU mode, you don't have a common field. Okay, so once you locate RU, then HECB user-specific fields for each assigned RU, there is one or multiple responded user-specific field to identify target stations for these RUs and its transmission parameters. So common field assign RU, how many users in that RU, and then you go to user-specific to find out for this RU who is assigned to, what all these transmission parameter is. Okay, so let's look at the HECB structure, okay? So I want to introduce some content channel structure and encodings, okay? To tell you how the HECB is transmitted, because that is very important for us following to understand the HECA and HECB, okay? So remember, you have, just for argument, we transmit 80 megahertz PPDU, 80 megahertz packet. We know all these legacy preamble, legacy STF, LTF, and LSIG, and the legacy, and repeat LSIG and HECA are repeat every 20 megahertz, okay? So that station can receive from each of them, can monitor 20 megahertz, decode them. Because so far, station don't know the bandwidth, don't know any information, okay? When you go to HECB portion, if you still repeat every 20 megahertz, it will be, the overhead of CGB will be large, especially when you try to transmit to the multiple users. So in other words, in the CGB part, instead of duplicate every 20 megahertz now we define the two content channels, okay? And instead of every 20 megahertz, we do the content duplication. Now we duplicate the two content channel. So in other words, the payload size of the HECB is twice of HECB part, because you don't duplicate every 20 megahertz, you only duplicate per content channel, okay? Two content channel, I will go to detail in the following slide, but each content channel is unique information and transmitted 20 megahertz, and for 40 megahertz, two content channels are duplicated. The station only need to demodulate up to 40 megahertz to get all the assignment messages. Okay. And from encoding point, for each 20 megahertz encoding together, so you first have common field, then plus CRC, you form the BCC encoding block. Then after that, remember they have user-specific field. So each user-specific field, two user-specific field, we encode them together. Then unless the last one, if you have a single user, then you have to pad it, okay, so that all this code block size is the same, okay? Oh, no, sorry, okay. Sorry, I take it back. Last user may encode it only separately if odd number of users. If we all have OFDMA cases or you have MU cases, different 20 macro SIG-B have the different content and they're not aligned, then we need to pad them together. Okay, in that case, you need to add some padding there. So go back to say we are seeing the two content channel. How this content channel is doing here, I want to show example here, okay? So for actually 20 macros, okay, so it's very simple. You have one content channel, common, and you have this OFDMA, you have user 0, 1, 2, 3, 4, 1, 2, 3 here. So have common channel to assign them. After that, all this per user information field in the same content channel in this 20 macros in the HE SIG-B. Okay. The second part, for example, HE 40 macros. Remember, we have this content channel. So now we still have OFDMA transmission. Look at the data portion. First 20 macros we transmit to user 0, 1, 2. Second 20 macros, in this case, is higher 20 macros we transmit to user 3 and 4. So because of we have two content channel, so lower 20 macros, the common portion we only located the lower 20 macros. The higher 20 macros, we only send the assignment information for the higher 20 macros, okay? And also the user assigned in the higher and lower 20 macros. So in other words, you can see there are two content channels, each of have different content in the lower 20 and 40, each assigned to its own specific 20 macros. So now what happens, you have 80 macros, okay? Remember, we have a two content channel, okay? Now look at the data portion first, okay? First 20 macros, we have user 0, 1, 2. Second 20 macros, we have 3, 4. And third 20 macros, we note as 20-2, have user 5. And the last 20 macros, we code 20-3. We code user 6 and 7, 8. Remember, we only have two content channel now, and we do the per 40 max duplication. In other words, assignment of the lowest 20 macros go to the content channel 1, which is sent to the lowest 20 macros. The assignment in the second 20 macros with the 20-1 go to the second content channel, so we send the content channel 20-1. Okay. The third 20 macros, which is 20-2. Okay. Each assignment, remember, we only have two content channel. Then assignment had to send in the first content channel, which is 20-0. Okay. Similarly, the fourth 20 macros, its assignment had to send the content channel, second content channel 20-1. In other words, the way to assign content channel is that start from lowest frequency order. First 20 macros assignment go to content channel 1. The second 20 macros go to content channel 2. The third 20 macros assignment go to content channel 1 again. The fourth 20 macros, there you go to the content channel 2. So in other words, this ensures you this kind of, you have only two content channel, then all this assignment go to this two content channel. Between the lower 40 and upper 40, the content channel are duplicated. So that sounds simple. Now you said, okay, how about we do the MU MIMO cases, okay? I have we have some users that the assignment over 40 macros, okay? Or more than 20 macros, okay? which content channel its assignment goes to, okay? In that cases, then you can distribute it, this kind of user assignment into two content channels. For the plot we're drawing below here, look at user 5, 6, 7, okay? They span the upper 40 macros, okay? So their user information assignment will be sent, can be sent with both content channel 1 and content channel 2, okay? So if you look at the content channel 1, which is sent at 20-0 and 20-02, so I can put the user 5 here, okay? Then for content 2, which is 20 carried in 20-1, 20-3, I put user 5 to register 6 there. So that the number of users roughly assigned the same. This we call the load balancing, so that to minimize overhead. Okay, so in other words, for large IU, you can distribute it over the two content channels. Okay, this is essentially what these are all the labels. Okay. Now we mention about, okay, the actually compression mode. Okay. We mentioned HE6 is have a common field, the per assignment for the assignment and the per user information field. Okay. There is one special case is for full bandwidth MU manual transmission. There is no need for IO assignment to the common field. There is no need for IO assignment. So the common field HECB can be saved because it's full bandwidth. Okay. So only thing you need to indicate is how many number of MU MIMO users. Okay. So this one indicates SIG-A. In that case, the SIG-B only contains the per user information field. You can evenly split it that. For example, you can user 0, user 1, put in content channel 1, user 2 in the content channel 2. So you can do this kind of load balancing, the same idea. Okay. So how this 80 macros, how this content channel or this Harman block is assigned, okay? This is doing in the common field in the HE6B, okay? Let's give an example. Remember, we have two content channel here, okay? If you look at the block, we transmit HE80 packet here. We have two content table. First one is content channel 1, respond to assign the first and third 20 macros. And we have HE content 2, which you can see is respond to assign the second or the fourth HE the 20 macros. Okay. By the way, in the 80 macro tone plan, there is one of the center IU26. Okay, it's cross both lower and higher. In these cases, this IU26, especially it's called center IU76, is signaling both of content channel. Okay. So how this content channel assignment works? So they use 8 bits to assign each 20 macros. So you look at this content channel, the first 8 bits allocate the first 20 macros, the second 80 macros assign the third 20 macros. Okay, you have 160 macros transmission, then you have another 8 bit to assign the third, the fifth 20 macros. So everything is duplicated. Every 20 macros which need to be going to the content channel. So you content channel Y, you have a 20 macro, you have 8 bit field to assign it. Okay. After that, you have 1 bit to indicate this center IU26. The similar structure in the content channel 2. The only thing is point to the different 20 macros to allocate. Okay. So how do you assign these 20 macros? Okay. Try to remember that this IU tone plan we draw there before I show in previous slides for different packet format, IU 20 macros, 40 macros, 80 macros. Remember this drawing? each drawing, remember, we have this layer. We have the IU26, then IU52, IU16. So in IU assignment table in 18 markers, for each 20 markers, in fact, it's mapped to this kind of older combination of each row and cross row. To give example, for this HE20, okay, HE20, we have 9 IU26. So the first entry in the IU assignment table, 0000, corresponding to all the 9 IU26 is assigned to each user. And each IU26 only assigned to one user. Okay. The next entry is another iteration saying, okay, I have all this IU26, but the last one, instead of assigned to IU26, but IU26 9 and 89 assigned to 52 to a user with IU52. So you can see all this table is trying to basically list all the possible permutations of this IU assignment. Okay. The things start to change. Go to the rows when you have IU106, okay? Now instead of one entry, now you say 0010YYY. What does it mean here? Now the reason is that, remember we say when you go to IU106 and above, there is possible this IU assigned to MU MIMO transmission. So this YYY indicate how many users in this Y06 IU transmission. For example, if the value of 000100001, then indicate there are 2 users in this IU106 IUs, okay? So here, the last row tells you how many entries there corresponding to how to mapping this YYY value to the different number of entries, okay? So essentially, each of these IE26, all the permutation is assigned by the IU assignment table. Now go to the once you assign the IU, which IU to transmit, you have to, each station needs to find out which IU assigned to and what the transmission is used, parameters for that RU. That's what the user-specific field is for, okay? User-specific content, depending on this RU, is used for the non-MU MIMO location. In other words, if that RU is purely OFDM, there only one transmission in that RU, or that RU is for the MU MIMO transmission. Okay. So if it's a single user transmission in the RU, you will see, oh, the first one, there's a state ID to tell you how many stations, who station ID, how this state is assigned, which station this RU is assigned, other than tell you number of special string, TXB informing, MCAS, DCM coding, all this information needed for this transmission scheme. Okay. The second one is for MU MIMO transmission. So not only you have to identify how many which this RU is assigned to, it have to have a special configuration to tell you which special stream you are located to, all this kind of informations, okay? This is the coding table, you can find the details, okay? And then the other bit to tell you how this RU is transmitted, the MCS, the 20 megahertz, this kind of, notice you don't have DCM because the MU MIMO transmission is for higher data rates. We don't use DCM for transmission. Okay, so far we have gone through all the most important part on the preamble part. Now we code the pre-HE modulate portion. Now we go to we call the HE modulated portion. Okay. Now we start to go to what we call the 4X numerology now. Okay. So HESTF, okay, we have legacy LTF for packet acquisition. Now, once we're switching from data to preamble, sometimes beam search or this kind of things, so the power will be changes, beamforming or MU-MIMO pre-coding. So we need to have another STF to condition the AGC to another DC estimation, okay? For this LTF is defined for the 4x numerology, but to reduce overhead, we have two durations. One is 4 microsecond duration for the SU, ERSU, MU, PPDU. And for the 2x, for the trigger-based duration, the trigger-based PPDU, we use a duration of 8 microseconds. The reason we use 8 microseconds is because of two things. The first is that, okay, when you trigger-based PPDU, we'll talk about it in the future, there are a lot of station transmissions that have different timing offset. So the spread of the delay spread is a little bit longer. The second part is that for the trigger-based PPDU, some RU, for example, RU26, maybe only have 2 STF tones. So if we use a 2x LTFs, if you use 4 microseconds, that tone number is too small. So use a 4x LTF, use 8 microseconds, use 2x numerology, and giving it more tones for better AGC conditions. Okay, then we go to the LTF part. LTF is for channel estimation. Okay. 3 different types of LTF is defined for AX. 4x LTF, basically the same duration, TF symbol duration as the data. It's 12.8. 2x is half of it. 1x is 3.2, same like 11AC and 11A. Okay. By the way, mathematically, okay, 2x LTF is equivalent to the 4x LTF modulated as every even tone. Okay, and 1x LTF is equivalent to that you modulate every 4 tone in the 4x tone plan. So this is the reason the sampling in the frequency domain defined equivalent to the repetition in the time domain. This is FFT properties. So in other words, for 2x LTF, essentially only populate half the tones. You do the FFT, then the time domain got to two time series which are repeated, then the trashed one, you get half of the sequence, which is 6.4 microseconds. Okay. So if we use this smaller, shorter LTF to reduce overhead. Okay. However, because the data tones need a 4x tone plan, so if you use a 1x LTF or 2x LTF, use a shorter LTF, receiver need to do the interpolation to estimate and populate tones. Okay. This is the 2x RTF generation, already highlights idea. By the way, most of this part plot is the same as 11AC. We'll not dive into the detail of it, but the most important part I want to tell you is that just like the first block, you see modulate every 2 tones, because for 2x LTF is equivalent to the 4x tone plan, which for the data that will modulate every 2 tones. After that, we apply the A matrix, just like AC, okay, for the different spatial stream, apply the CSD, we do a spatial mapping, we do IDFFT. Then after that, the truncation, 1/2 of time symbol, that's the place you generate half symbol, 2x symbol, which is half duration 4x symbol. Because FFT property of only modulate every 2 tones, ensure that this 4x symbol is duplicated, repeat every half symbol 6.4 microsecond duration, so you can truncate it and become the 2x symbol duration, 2x LTF duration. So the rest of the same as the Lexi 11 and 11AC. Okay. So the pioneering LTF, okay, they're also pioneering LTF for frequency tracking and phase tracking, okay. For the SU, ERSU, MU PPDU, and the trigger-based PPDU for non-MU MIMO transmission, LTF, the single stream, which is the same like AC, and not go over it. The special thing is about upping MU MIMO, will you actually trigger PPDU. In this case, the same RU AP receive overlapping signal from multiple users. Each of them has own frequency and phase arrow. So it's much more difficult for AP to estimate and track multiple frequency and phase arrow in MU MIMO cases. So because of that, there are some special treatment for HELTF pioneered for upping MU MIMO. For example, if with the y-axis LTF used for full bandwidth upping MU MIMO, because LTF is so short, the phase drift will be small. You will not use pioneers. Or you can use a single stream pioneers, just like the other transmission. Or you can use a frequency domain mask. Basically, you have no pioneers, but use kind of frequency domain mask to separate the channel of different users and do a channel estimation. This way is less likely to use and not where any products use it, so not go to the detail of it. Okay, most products, if you use it, probably use the first one. Okay. So this is a summary of the HELT and the GI types. Okay, I mentioned we have a different type of LTFs. Okay, and the different type of GIs durations for different environment. Okay, you see y-axis LTF with 0.8 microsecond GI, 1.6 microsecond GI, 2x LTF, 4x LTF. In the rule of thumb, generally speaking, the mostly common used combination is 2x LTF for all the non-triggered packet plus 0.8 microsecond GI, because this is for most of the environment. Okay, for the actually trigger-based PPDU, because there are multiple station transmission coming up, their signal is not perfectly aligned, so we need a longer GI to assign the timing difference between the different users. For the actually trigger BPDU, the more common user GI is 1.6 micron GI. In fact, you look at this table, we're not even define 0.8 microsecond GI for actually trigger BPDU. Okay, so the common use for actually trigger BPDU is the 2x HELTF with the 1.6 microsecond GI. Okay, if you do the full bandwidth upping MU MIMO, most likely use is y-axis LTF with 1 microsecond GI. Okay, so that's the mostly common used mode. Okay, the attribute standard specify all these mandatory continuous optional required mode. You can read the details. Okay, so now let's talk about the data portion now. Okay. Data portion, just like AC, we support BPSK, QPSK, 16 QAM, 64 QAM, 250 QAM, and we add a new 1024 QAM and the DCM in the modulation. And the encoding, the same as AC, we support both BC, the LDPC. The only difference is that now the requirement, what's a mandatory, what's optional requirement for LDPC and BC changes. There are a lot of detailed rules. I will not go over it. You can go to spec. For example, it transmits 20 megahertz above bandwidth. You have to use LDPC. Use 124 QAM. You have to use LDPC. There are a lot of details. Feel free to read spec. Okay. So here I give the MCS table. In the right-hand side, you can see for each MCS, depends on DCM, enable, not enable, you have a different rate because DCM duplicates the tones. Essentially half the data rate we use enable the DCM. Okay. So as we just talked about it, DCM essentially duplicates the tones. Okay, on the high level, you duplicate the tone, transmit the same information on the tone in the two different subcarriers. By doing this, you basically half the data rate, but half the data rate you got link budget gain and also diversity gain because the frequency diversity, because some part of the tones may have better fading than the other ones, so they have frequency diversity, and also interference diversity if some of the tone is heavily congested by some of the interference, then you have another tone. Okay. So usage of DCM is applied to the SIGB and data portion, and we only define DCM, BPSK, QAM, and 16 QAM, and only limit 1 to spatial transmission, and not used for downlink, uplink, MU, MIMO, STBC, because DCM is mostly for the lower data rate. Okay. So DCM, as we said, the two parts, the first one, duplication part, is easy. Now we have a different mapping. You duplicate the content of one subcarrier or tone to different tones. Then in order to get diversity, then the next tones you want to change slightly. For example, SK is the QAM symbol, we send to separate K, okay? With duplicated, for example, suppose SK is BPSK modulated, with duplicated for the DCM transmission, which means there is a tone that the certain distance away, then times rotation of -1 times K times NSD, okay? So in other words, it's not exactly the same repeat as the previous one, but have this +1, -1 alternating. This is, by the way, main purpose to reduce the PAPR. For the QPSK, another tone, when you repeat it, instead of send the same one, you do the conjugate version of it. For the QAM, with the dual DCM mapping, you swap the bit 0 and bit 1, and bit 2 and bit 3, when you do the original version and the repeated version. All these things try to achieve the diversity. Okay, so let's put all of them together, then this is actually data transmission field, okay? I put the block diagram here. By the way, there are block diagram for different modes, different coding scheme in the spec. Feel free to go over them because they are exactly the same as AC in many cases. So I will not go to the details here. Essentially, you go through the pre-FEC, FEC padding because you need to align to certain boundary. We'll talk about it in the future. Then we do the scrambler, we do RGB encoding, we do the post-FD padding to align to the symbol boundary. We split into different streams, okay? Then we do the constellation mapping, okay? Then we do the LDPC tone mapping because the LDPC have to interleave to different tones, okay? Then we do the pre-SD to split into spatial stream. Then we do the per stream mapping to split into 18 makers. Then we do the IFFT, the user GI, then we go to analog. So the process is similar as AC. Okay. Now the last I want to spend time talk about package extension because this is new. There are some question about in the Q&A. So what's the downside of the going to 4x tone plan? So one of the downside you go to a larger FT size. So which means you have the last symbol processing, you need more processing time. Okay. We know that 11.11c, all this kind of thing, many of transmission requires the shift response. Basically, need to send AG after shift time, 16 microseconds. So because of larger FFT size, 4x numerology, and higher peak data rate, now receiver cannot meet that timeline. So in order to relieve that one, so there's something called package extension was added, okay? So it's called PE. PE field intentionally can add a time of 0.48, 12, 16 microseconds to provide relief to the transmitter, to a receiver processing time. Okay, package extension is the same power level as the date symbol field, and basically the same bandwidth as reused by the date field. Okay, the content is kind of arbitrary because it really just provides the relief of the processing time of receiver. So how this is being done, okay, for the packetization, I want to introduce a pre and post FCC padding, okay. So what really happens is when file receives the information between the MAC layer, okay, this is called the information bits, okay. It pads do some pre-FC padding so that when it do the scramble and LTPC encoding, it will add the third one of the full boundary of the packet, okay. That full boundary is called, we use a factor of A. A equal to 1, basically this means after the information bits and the pre-FC padding, you only fill 1/4 of a packet. If A equal to 2, then which means after the information field, after encoding with information bits and the pre-FC padding, you fill half of the packet. Similar thing for the A equal to 3, which is 75%, or equal to A equal to 4, which is 100% filling of the packet, okay? Then the rest of it done through a pre-FC padding pad, so that when the file transmission, they have enough coded bit to fill into the entire OFDM symbol. The reason why we separated this pre-FC padding and post-FC padding is this, okay? Post-FC padding don't need to be decoding. So in other words, post-FC padding can be considered part of the time to provide relief to receiver timing, okay? Pre-FC padding need to be decoded. So we want to pad to the certain boundary so that we can indicate receiver side what the receiver time need to be, because this have to be certain boundary, not arbitrary boundary. So this is the reason we have this pre-FC padding to one of these boundaries called represented by the A, then post-FC padding basically pad to entire OFDM symbol. Okay. So how do we determine the padding time, actual packaging time? In fact, it's a little bit complicated, but logical is like this, okay? So receiver tell the transmitter what the processing time is needed. This is conveyed by some variable called the nominal packet padding, okay? Nominal padding, as we mentioned, depends on two things. The first one is post-FCC padding, okay? As we mentioned, post-FCC can be counted as relief time, okay? So, and another one is nominal packetization time, PE, okay? Nominal PE is negotiated by the transmitter receiver telling me, okay, how much time I need, okay, how much relief time I need, okay, you would tell me, okay, then the receiver will now look at the nominal processing, look at how much pre-FCC padding, then determine what the nominal PE will be. Nominal PE will be the minimum PE is needed. In other words, from the MAC, it tells you what the nominal packet padding will be and pre-FCC padding of A. So example, the from MAC telling you need to packet 16 microseconds. By the way, there are 12 microseconds is the pre-FCC padding is only 1/4 of it, equal to 1. So there are 12 post-FCC padding receiver can use. In this case, receiver think, maybe can only put the full packetization there. So that's a receiver, that's a transmitter will determine the nominal PE will need it. The actual PE effect will be has to be at least longer than the nominal PE, so that receiver have enough time to process it. Okay. For trigger-based PPDU, everything is simple. Why? Because PE determines the AP. AP is the receiver. He can, based on his computation, to know what the packetization value will be. all this computation is now needed, and AP just send it in the trigger frame, which is schedule method. So this plot give you example. Okay, so I give you example in the cases for the HESU and EISU when the nominal padding is 16 microseconds and the actual PE transmission is the required PE, which is nominal PE. So in other words, if somebody tell you, Mac tell you, I need a nominal packaging of the 16 microsecond, and somebody look at the top of this plot, Mac tell you is AQ to 1, basically saying pre-FT padding is only packed 1/4 of a packet, then the transmitter will say, okay, there are 12 microseconds of post-FTC padding, so can be used by the relief. The total requires 16, so I only need to pad the 4 microseconds. So you only apply the 4 microsecond PE there. Okay. Similar thing if AQ to 2, then pre-FTC padding encoded bits filled half of the last OFDM symbol, and the required time is 16 microseconds. Then it compute, oh, I can put 8 microsecond actual PE there. Similar thing for different values, AQ23, AQ24. So this is the reason how the nominal PE determined and how actual PE is determined. Okay, before we end this section, let's revisit EISU. Okay, EISU, we are saying it's an extended range SU. We want to plan the power boost. We want to provide the actual link budget benefit. We said we'll do a 3 dB link budget in the preamble part. We are doing that by doing a 3 dB power boosting of ST and STF. Okay. We also do the repeat of the repeat L6 of L6. We got 3 dB boosting there. We also do the 3 repetition HE6A. Repeat is that 4 symbol, is that 2 symbol in a regular packet, so get 3 dB there. Okay, so all this preamble is 3 dB there. Okay, then do the data portion. Okay, STF, HESTF, HELTF, both by 3 dB. The data portion, we can use the DCM to half the data rate to get 3 dB. Or you can only transmit 10 megahertz, then use the DCM. In this, your data rate is 1/4 of it. In that case, you can get another 3 dB there. So total data portion of the EISU, if you want, you can get 6 dB. So this is the way we define EISU just for the extended range. Okay. Okay. So this is the conclusion of topic 4. We go to all the details of HEMU PPDU and the usage. A lot of detail, but we go over the high level of the usage. Okay, let me do a quick Q&A to the transmitter. Okay, in which condition do you have 0 GI for interval? Okay, we don't have 0 GI. Okay, so there are 2 meanings here. I want to be clear what we are saying. Okay. I understand your question, 0 GI mostly represents saying there are no GI. Okay, no GI doesn't work for FDM because for the orthogonality, to ensure orthogonality or FDM transmission, you need to add the GI to ensure the delay spread doesn't get into the next symbol. So GI is always needed. If you talk about the 0 GI, which is has no power in the GI part, 0 GI is not used for the 11ax data communication. There is something called 11az, which for the ranging, enhance the ranging. In the 11az, when for the security purpose, they introduce something called 0 GI. By the way, you still have a GI interval, just don't transmission any power in that region. Okay. So that's seems like all the questions I can see from the inbox for now. Okay, let's take a probably 3 minutes break and we can reconvene at the 11:17. Okay. Okay, let- let's resume the discussion. I think that in the previous section, we have highlight what the main 11AX5 feature is, and its tone plan, numerology, RU concept, which are very important, by the way, for to basic understand basic for the 11AX spec. We also go to the very level of details about different PPTU, the different usage at each segment of the PPTU. So the last section, we want to talk about a little bit of file operations of this all the knowledge we have learned so far. Okay, especially we want to talk the trigger, we want to talk about transmission, we want to talk about preamble punching and special reuse. Okay, so triggered transmission. Triggered transmission is one of the very new concepts introduced the AX. Okay. Essentially, it can enable the uplink OFDM and MU transmission. By the way, it also other benefits for scheduling, for the power saving, all these kind of things. Alfred will talk about in the future in the next section. So if you look at the from 5 point of angle, will enable uplink OFDMA, uplink MU MIMO. Okay. So enable multiple stations to transmit simultaneously. Okay. In order to happen, you have to schedule it. Otherwise, all stations try some own will be a mess. All the signal will collide with each other. So in order to schedule this, AP will call something called the trigger frame. Okay. Trigger frame will identify which client, non-AP station, will participate in the uplink OFDM, uplink MU MIMO. And it specifies all the necessary mode information, OFDMA, MU MIMO, IU size, location, NSS, number of spectral stream, MCS. It will also talk about the power control. I will talk about it later, okay? So yes, the detail of trigger frame content will be discussed in the next section, but I want everybody to realize from PHY side, okay? The trigger transmission is scheduled transmission, okay? So many things need to be defined, and there are many uniqueness of the trigger transmission from PHY angle. The first thing uniqueness from PHY angle is power control. Because all the different users transmit simultaneously, it transmits the trigger frame from AP. So how to avoid their interference to each other? Okay. If the close-by devices mask the the clients which have poor link budget reach far away, okay. So to order to solve this, the important part is AP go to schedule each stations in uplink transmission. Then they have to schedule the MCS transmission. They have to ensure each station transmitted the right power to meet its assigned MCS, which is assigned scheduled by the AP. So AP control everything, specify who transmit, what MCS to do. He need to provide the information to the client to ensure that each client will meet with the right transmission power to meet this MCS and don't interfere with each other. So on the high level concept, this is achieved by the power control by AP including the following information in the trigger frame. It tells the downlink transmission power. By the way, this is normalized by the 20 megahertz because sometimes client, when you read the trigger frame, he doesn't know the entire bandwidth of packet. At least he knows it's 20 megahertz. So the downlink dropper will be powered by the 20 megahertz. Okay. Also, AP will specify the target ISI for station and it's assigned MCS. E is assigned RU. Okay. So in other words, AP tell you this station 1, I will effectively transmit MCS 5 and coming here at the signal level, ISI level minus 72 dBm. Then the station, when he got these messages, he will first compute the downlink path loss. Because he knows the AP transmission power from trigger frame, he can also measure the downlink SI. By the way, everything is normalized to 20 megahertz. He can compute the downlink path loss. And once he knows the downlink path loss, he knows what the target SI that AP required him. He assumed the path loss, the downlink, and uplink the same. You sum them together, you got the transmission power. Okay, so he will use this transmission power to transmit his trigger-based PPDU. There are some details there. For example, if AP station will apply the beamforming, then he take the beamforming gain into consideration, we compute the target SI, this kind of thing. And AP also need to report uplink transmission power headroom to assist AP to future MCS adjustment. Why is that? Okay, the reason is that we see AP power control the client to certain power level to satisfy MCS. There are two scenarios, okay? The first one is AP let client transmit 1K QAM, for example. Client to the computer power target SI. Even if he transmits he find out is transmitted at the peak power, he cannot meet the target SI. So he need to tell the AP, by the way, I reach my power headroom is 0. I cannot go higher, so you better consider drop my data rate. The other possibility is that opposite of it. The AP power control client do the computation and find out the transmission power is only 0 dBm. Client can tell AP, by the way, I can transmit another 10 dBm higher, then you better give me assignment higher MCS. So there is the information here that the client need to report TX power headroom to assist AP for the MCS transmission in that scenario. Okay, let's look at a little bit targets there. There are a little bit of detail there. For example, how they target the SI specified in the trigger frame. There is a bit mapping there. We not go to the details. There is another thing about power control range and accuracy. Okay. AP specifies some target SI for the client, but there are always some errors. Client measure signal strength error, how accurate control transmission power. So there are kind of the spec define two kind of devices. One is class A, which means everything power control, everything is within 3 dB accuracy. This is the most of the devices. There is another devices, basically dirty, cheap devices, have a power control accuracy, for example, plus 9 dB, very low cost limitation. In that case, for AP schedule it, need to consider this margin. There is another requirement for the trigger-based transmission. We mentioned all of them transmit simultaneously transmission in response to a trigger frame. So essentially, they use the term as OFDMA, orthogonal frequency division multi-addressing. Okay, so the first word is O, orthogonal. To install the orthogonal, which means you want to avoid intercarrier inter-symbol interference, each symbol need to pre-correct its transmission frequency so that the frequency offset is small, they're still orthogonal, and also need to pre-correct its time so that the different area between different stations plus their round-trip delay difference still within the GI interval, so that with the AP do the FFT, we receive the OFDM symbol, all the signals still be orthogonal. So because of this, so all the time pre-correction, there is certain requirement. We tried the station to transmit the start time after trigger is 6, which is 60 microseconds, within plus minus 0.4 microseconds. This is the accuracy requirement after the end of triggering PPDU. Okay, So to ensure everybody transmits at the same time with accuracy of plus minus 0.8 microseconds. And it also requires free pre-correction is the frequency and sampling time so that the residual error after correction is less than 350 hertz 90% of the time given in the certain channel condition, for example, minus 6 dBm AWGM. Okay, so specify that to ensure all the quality of the trigger-based PPDU and to ensure all the transmission are not interfered to each other. The second concept is preamble puncturing. I think I see some question about how the puncturing is doing there. Okay, I have a drawing here. Okay, before the 11 AX. Okay, when some station do the CCA find some channel is busy, he had to shrink his transmission bandwidth to avoid that interface channels. Okay. In the drawing here, and in the drawing, I'm showing in the plot in the slides there. Assume the bottom one have a primary 20 megahertz. Before the 11AX, if they find the third 20 megahertz is busy, before 11AX generation, 11AC can only transmit a lower 40 megahertz towards the third 20 megahertz, okay, which is interference. In the 11AX, you introduce the 11 preamble puncturing so that you can still transmit 80 megahertz PPDU, just you don't transmit in that interference 20 megahertz. By the way, it's called preamble puncturing because mostly important part is the preamble puncturing part. The data portion is achieved by not assigning it. So as far as the preamble puncturing is part, data portion you don't assign in that interface region, then you achieve the purpose. I want to emphasize the 11AX only supports preamble puncturing feature using OFDMA. In other words, we have to assign the RUs in this drawing here at each side of the puncture channel to different stations there. So he treats this as OFDMA transmission. The user that above the puncture channel go to one station, user below the user assigned to different station. Always because in 11EX, OFDMA, each station can only assign one RU, okay? So you can only assign one RU either above or either below, okay? This thing will be upgraded in next generation 11BE, which single user transmission prior pump will be support, okay? Through the multiple RU, when station can receive multiple RU. But that's the first, for future generation. For this generation, just remember, you can only do the preamble puncturing in the OFDMA. Okay, so as we just said, SU and EISU format cannot support it. You can do the MU PPDU to support it using OFDMA. Pre-HE portion is now transmitted on 20 megs subchannels, or those so-called puncturing channels. IUs within those puncture channels are not assigned, so to avoid that channel, okay? So what happened to a trigger PPDU, you will ask, okay? Trigger PPDU in fact is naturally supported because in the trigger PPDU, each client only transmits preamble in the 20 meg subchannel which assigned its RUs in. And AP can simply just not locate any client in 20 megahertz subchannel, and the preamble will naturally punctured. In other words, preamble puncturing, this kind of operation is naturally supported in the trigger-based PPDU. You only need to define for MU PPDU for downlink or DMA. Okay, so how preamble puncturing is indicated? Okay. So it's called preamble punching. Remember, HECA portion is duplicated every 20 megahertz. So you don't need to indicate anything in the HE 20 megahertz. If that channel is punctured, you don't need to do anything. But HE sig A part will tell you that the bandwidth field will tell you in the HE sig B portion which content channel is punctured. Remember, we have two content channels there. It's duplicated. Okay, in the first and third one, 20 megahertz carry content channel 1. The second and fourth 20 megahertz carry the content channel 2. Yes, one of these content channel can be punctured. Okay, so the HE sig A will indicate that. So when they go to HE sig B portion, they will know which content channel is punctured. So you go to another copy of content channel 1, content channel 2 to find the not punctured content channel and get all sign information. Okay. The last topic I want to cover today is spatial reuse. Okay. So the goal of 11B AX HE trying to increase the more efficiency in the highly dense environment. Okay. Essentially, it means besides all these PHY improvement, this kind of things, multiplexing improvement, another important part is try to give the station more chance to transmit. Or in other words, most technical words to describe this, most spatial reuse among different OBSs to allow them to transmit simultaneously. Okay. So this is achieved by two things. The first one, you need to know the signal, a transmission packet, is from other BSS. Okay, this is achieved by beta counters in the HECA field. Can also be achieved by looking at the MAC field, MAC address field, this kind of thing. The other most important part is interference measurement. Okay, so today we'll talk about the two spatial reuse fields defined AX. One is called OBSS-PD-based spatial reuse. The other called PSR, basically parameter-based parameter spatial reuse. Okay. OBSS-PD-based spatial reuse, in fact, idea is very straightforward. The idea is that before the AX, CCOA is considered idle. CCA basically the clear channel assessment. The client trying to look at the channel is measure if there's a signal there. So there is the ED level minus 62 dBm. I didn't mention here because it's mostly reused between the OBSS. Another most important part, generally, it's called packet detection. Okay, the packet detection level minus 82 dBm specified in the spec. So before 11AX, if you see the channel is minus 82 dBm, you cannot transmit. Okay. Now, this you can find depending on deployment scenario, different configuration. This may not be the best way to optimize the network throughput. So the idea is that it's possible I can adjust the text power that to achieve different threshold. That essentially is the idea of OBS-PD. Look at the power, the plot in the right hand. Essentially, you have a shaded area, and you have a line there. The line there is the OBS-PD level. Now, instead of one straight line of PS level, it's basically saying it have a function of the TX power. Okay, so if a TX power is very large, yes, the peak PS you can only use the PXPD minimum. Okay, once you start to drop from a reference power, you can exchange almost dB by dB by dropping the TX power with OBS-PD level. Okay. Now, of course, you cannot OBS-PD level too low. Beyond a certain time, then you reach OBS-PD max. You can no longer to drop it. Okay. So this essentially, that equation there will not go to the detail, but the main idea is beyond certain range, you can exchange between the transmission power of dB to BD exchange for the OBS PP level. So that if you transmit less power, you cause less interference to other people, you have more chance to special use to transmit. So even more details there. There are two different kinds of OPS-PD to define. Okay, one is called special reuse group. Okay, the other is non-special use. It's called SRG. The other is non-SRG. So intuitively, SRG is a bunch of APs that deploy together. Okay, they have a common goal to optimize the network, enterprise network, those kind of things. So we all agree on that by increase the OBS's PD level, that will increase the benefit for everybody. So we will do it. So in the SRG, it's called SRG OBS PD. Okay. For the non-SRG PD, you will, as client, don't have a try to disable the special use, okay? And also the level of the OBS PD mean is agreed among multiple APs. So every client need to be agreed to, okay? So there's another type, non-SRG group, so that they don't know what the upper is, you don't know what the AP is, you don't have a coordination with them. In this case, okay, there's no negotiation, there's no coordination in these cases. In this case, non-SRG OBS PD, you have a little bit more freedom that you can turn off the OBS PD disable if we want, okay, on packet basis. And OBS PD meaning level is the fixed, specified by the spec. Okay, so that's mainly the higher level idea between the SRG OBS PD and non-SRG OBS PD. Okay, station can choose to operate on either of them. Okay, I go to all the details here. Then essentially this is what this two table tells you. If we at the right-hand side, SRD-based OBS PD, basically the enterprise deployment or other several AP who have common coordination that want to work together for common good, okay. It can specify for example, when the special use is enabled, okay, when the value is 1, the OBS minimum PD is determined by the parameter OBS PD minimum offset, okay. The OBS max is also minus 82 depends on OBS PD max, okay? On the other hand, if we have the non-SRG ones, you see all these values fixed, okay? OBS median is minus 82 because there's no negotiation, no agreement, there's no kind of things, you don't know what the AP is, so at least you need to satisfy minus 82. If you want to go to lower, they have to go to the SRG. Okay. So there's some question about, I see the QA, what's a good application of SRG? Generally, I would say it's the deployment, this AP is with your control, so you all optimize the parameter for the common goods. So mesh or the enterprise network, then you can define the SRG OBS PD. Okay, so the first one we talk about OSPD, very straightforward. You drop the TX power in exchange for the OBS-PD level, more transmit opportunity, okay? The other one is called parameter-based special used, okay? So special use parameter special use, PSR. In this case, 11ax is only applied to the triggered space PPDU. In other words, the special use transmission will again adjust transmit power, but instead of based on the very fixed OBS PD level that's determined by the signaling or the spec, it's based on the parameters in the HECA of the OBS trigger-based PPDU. O is preceding trigger frame. Okay? So what it really means, let's slow down a little bit and look at what happens when we have a trigger-based transmission sequence. First of all, when I have trigger-based transmission sequence, AP trigger frame, okay? This trigger frame is carried called a PPDU, okay? This one is carried by the trigger preview. In this context, we talk about spatial use, it's called the PSRR PPDU, okay? PSR reception PPDU. This is by the AP to specify all the trigger-based transmission. It also has the PSR spatial use parameters. Okay? Once the client receives that trigger-based PPDU, it will transmit uplink trigger-based PPDU. Okay? Uplink trigger-based PPDU in the HECA way of uplink trigger-based PPDU will specify the parameters that can be used for the spatial use to see how much interference it can cause me, and you try to do a computation, try to avoid of interference to me. Okay. So the third station from OBSS, once he received the PSR PPDU trigger frame and receives the ongoing actually trigger-based PPDU, he can transmit PPDU in the spatial use. This PPDU is called PSRT PPDU because this is the PSR transmission T represent transmission PPDU. Essentially, this PRT transmission is somebody transmitted by an OBSS client. OBS station can be the AP at the client. Sorry, I keep saying client, but in reality can be by the AP. So PSRT PPDU is transmitted by the OBS station that can satisfy the PSR requirement. Okay, and by the way, everything transmission has to be terminated by the original trigger-based PPDU. So how this this thing works? Okay. The concept is this. On the right-hand side, I have a plot. Okay. You have AP, which is station 2, then want to trigger transmission state 1 in the uplink. So this is one BSS. On the other hand, you have another BSS, which is stage 3. You want to do a PSR transmission to state 4. Okay. In the same time, in the PSR reuse. So now look at the left-hand side. Okay, first one, the state 1, send what's the PSR packet is the PSDU1 from state 2, state 1, which is a trigger frame, carries all this information. Okay, so reuse information, PSI information, TX transmission power. Then the state 3, which is another OBSS, will try to measure the path loss from state 2 to itself. How to measure path loss? Remember the trigger frame carries the TX power and information of the used for the TX PDU1 by the state 2 AP. So he needs a transmission power. So measure 3 based on transmission power and also measure measure its own SI, and also from trigger frame, he know what the PPDU1 transmission power is. Boom, he can compute the downlink transmission power. Okay, he can compute the downlink path loss. Now, stage 3, still the station want to reuse. He lessen the PPDU2 transmission. Okay. He decode HECA and get reuse transmission parameters. and the power level. Okay. Now station 3 want to see if it can transmit on PPDU3 on top of the PPDU2 transmission. How do we do it? State 2, they want any interference during the PPDU2 reception to be less than the power P. Okay? If the state 3 somehow knows this, then state 3 can transmit the power PPDU3 on top of PP2 if it can make sure his transmission power minus the pass loss from state 2, which is the AP to itself. Remember, we just computed this when the AP transmitted during the PPDU1 cases, less than the desired interface level that the AP state 2 want to have. Okay? So if state 2 somehow commands station to send out his PP2 to satisfy this interface between this transmission power, then it happens. Okay? So in other words, the next pages will tell you, okay, what the AP, triggering AP will put in the trigger frame, tell you what its TX power level is and its accept interface level is to all the BS stations. Okay, all the BS stations based on the TX power will compute the downlink pass loss. Based on the interface level it can tolerate it can compute its transmission power, then to transmission power. So all the station I can provide the equation there. If you work out equation, the station will transmit based on SRP and minus its receive SSR of the PSR format. Okay, once you transmit all these things, then it can determine his transmission power. Okay, so by the way, PSR-based spatial use a little bit more complicated. There are a lot of equations there you can work out in the future. Okay, for the details. If you have a question, feel free to talk about in the future. Okay. Again, now we finished some of the questions. We finished the topic 5 and also entire section 5. If any question, feel free to submit the Q&A. Yeah. Okay, so far I see none of them. So if now just test your knowledge, think about, okay, what the power control requirement, what the spatial reuse type, okay, why they're needed, how do we need it, this kind of thing, okay? I see a question, has anyone implemented PSR? Good question. I cannot speak for implementation because anybody implementation is different. So as far as I know, most of the many, I cannot say most or many, as far as I know, many implementation doesn't implement the PSR because very complicated. Yeah. Okay. There may be some devices when you implement it, I don't know. Yeah. Okay. Okay. Any other questions? Okay, I hear none. Maybe I can come back to the Jennifer. Maybe you can take over, Jennifer.
Yes, thank you. Thank you very much, Ben. And thank you, everyone who joined us today and stayed until the end. Thanks, Ben, for a great presentation. And thank you, Alfred, for all of your help as well, answering questions. As noted earlier, the on-demand link for today's event will be emailed to everyone in approximately 2 hours. Before you leave, we ask that you please complete our feedback survey via the survey tool at the bottom of your screen. And please remember to come back tomorrow. We're going to start at 9 a.m. Pacific time and 12 o'clock noon Eastern time when Alfred will focus on the MAC layer of the standard. So thank you all again for your time today, and we'll see you tomorrow. Thank you.